Hi, Dr. Anthony Revis here with Watch Me Work It. I'm going to do some reaction quantities and limiting reactants. So here it is. If we consider the following reaction of zinc plus hydrogen chloride to produce zinc uh, chloride, which is the two state of zinc, and hydrogen gas. So we write, first thing you're going to do when you see these types of reactions, make sure it's balanced. In this case, I've already balanced it for you. So we have the balanced equation. So here's what we're going to do. Calculations. Ready? Calculate the moles of HCl needed to react completely with 8.25 moles of zinc. So when we see a problem like this is our given. When we see these, they're all classical dimensional analysis. It's 3 sig figs. I'll just keep an eye on that, make sure we get that right. And this is my given. So I'm going to start with my given of 8.25 moles of zinc. And so I'm going to do a crossbar here to do this problem. And I'm going to say I have zinc here. Okay, and so it's moles of zinc. So we go moles here of zinc. And what we want to do is know how many moles of HCl. Okay, so if that be the case, we can always go mole to mole right away, mole of HCl. And that should give it to us right there. Now we have to fill in these numbers. These numbers always come from the balance equation. Always balance equation, nowhere else. Don't look for them, don't calculate them. I mean, don't go get them from anywhere else. You simply look at the balance equation. So if I look at the balance equation, I see a 2 in front of HCl, and in front of zinc, I see only a 1. So this always comes from the balance equation. So I simply look at it and read these, nothing more, no calculations here at all, and I'll get my answer right away. And this answer is going to be 16.5 mole, 3 sig figs, and I'm good. This is my square in number, final answer here. Okay, the next one, calculate the grams of zinc chloride produced from 0.2387 grams of zinc reacts completely. That means you use it all up. Okay, so let's just see what we do. So let's start with our given. This is our given. And we have 3 sig figs in that given. So we write it 0.238 gram of zinc, and grams, we don't want grams, so we put it on the bottom. And that's how we do dimensional analysis on it there. So write the same thing here. So grams always will go directly to moles. You can't go gram to gram. Okay, you have to go through moles when you have these types of problems. And so now I'll take moles of zinc on the bottom here because it's on the top here. I don't even think about it. I just do it. I see it and I repeat it diagonally. And so this is going to go to moles of zinc chloride. But I'm looking for, this is mole, by the way, nice, neat writing. And so here, moles of zinc chloride will go to grams of zinc chloride. So now I'll just go back and put all these values in. I'll look on the periodic table and look up the molar mass of zinc, and I see that 65.39 gram per every 1 mole. There's always 1 there. This I read from balance equation. No math here, just read. So I look at the balance equation, I look in front of zinc chloride, I see a 1. In front of zinc, I see a 1. That's what I see. Don't think, just write when I put the balance equation. Don't look at the molecules, the atoms within the molecules. Just look at the balance equation. That's it. Don't multiply anything, no math. Read what you see in front of each of these species, and you'll get it right every time. The biggest mistake made here is people start doing all types of calculations here. They get the right answer, but they have the wrong ratio and they lose points or something like that. Okay, so here we get gram per mole of this. This is the molar mass, is always per 1 then. I do my molar mass calculations, which I assume you know how to do a molar mass. 0.29 gram per mole. If you run this through your calculator, assuming I put in everything right, you should recheck your calculation, recheck my calculation in case I made some mistakes. This is the right process. So this is my square and answer with 3 sig figs. So I feel good about that. Let's do another one here. What if I dissolve here lead 2 nitrate? That means lead have a positive 2 charge on it. Lead 2 nitrate. And this is the balanced equation for it. So we ran the reaction, we balanced the equation. So this is balanced. And what we know then is that our stoichiometry is 1 to 2 to 1 to 2. Those are my stoichiometric ratios. I just keep an eye on those. So calculate the grams of lead 2 iodide that can be produced from 5.00 moles of potassium iodide. So that's a problem. Calculate the grams of lead 2 iodide that can be produced from 5.00 moles of potassium iodide. So this is my given. I do set up to do a dimensional analysis using this as my given 5.00 mole Ki. Keep in mind, I'm looking for grams here, so I'm going to write that out here somewhere so I can keep an eye on it. So grams, and it's grams of what am I looking for? Lead 2 iodide. So it's going to be PbI2. I just want to keep an eye on that somewhere so I don't get lost. So this is going to be moles automatically. As soon as I see this, I write it right here. Moles Ki. Okay. Without thinking about that at all, I just write it. And I can go straight from mole to moles of something new. So this is mole Ki to mole of PbI2. That's headed in the direction I'm looking for. That's why I wrote it there. And so now I can go, I see this mole here, automatically write it on the bottom. Don't think, just write it on the bottom. PbI2. Hopefully your penmanship is better than mine. Let's go to grams, PbI2. I go back, these, I just simply read from the periodic table. I read in front of PbI2, I read a 1 for stoichiometry. I read in front of Ki, I read a 2 in front of it. I Google or calculate my molar mass. And I'm just going to put another 0 here. And so we go like this. That works out. The math works out. And what I obtain is 1.15 3 sig figs because I see that I have 3 sig figs here in the given. That's good. 1.5 times 10 to the 3 PbI2. Okay, so you just watch me work through these so you can do it too. All right, so how about this? Calculate the grams of lead 2 iodide that can be produced from 75.00 grams of potassium iodide. Therefore, this is 4 sig figs. All right, so we have this. And what are we looking for again? Calculated grams. I'm going to write this out here so I can keep an eye on it. Look for grams of PbI2 from that number of grams. Okay, potassium iodide. So this is pretty much same type of process, isn't it? Yep. So we have 75.00 grams of K potassium iodide. So I'm going to go grams directly here because automatic, no thinking here, that's automatic. And grams always go to moles. They never go gram to gram, so you can bet on that. So then we have moles of Ki. And wow, this is a good place to, to go ahead and, let's see. I took moles, yep, got that right. And now I need to do a little bit of a inner conversion here, don't I? So this is mole, can't read them on right, moles Ki can convert over right here to moles of PbI2. I'm happy with that. That's mole to mole. Not very neatly written here. And so now I go mole. What am I looking for? Moles. I'm looking for PbI to grams, and moles can take me to grams of PbI2. I go back and plug in the molar mass of this. It's 166. I Googled this or I calculated it on from values in the periodic table. This is a mole, by the way. That's really ugly. I'm going to rewrite that so we can see exactly. Say mole Ki. So I read from the periodic table. Nothing fancy, no math. I look at the periodic table. I see a 1 in front of this. Ki, I see a 2 in front of that. That's all I do here. No fancy math, nothing at all. Read. And so here, grams of PbI2, the moles of PbI2, that's a calculation I do to get the molar mass. So I do that, or I Google it. So when I punch all these numbers through, what I get here is 104.1 when I round it off to the proper number of sig fig grams of PbI2. This is my square N final answer. Let's do another one here where we do specifically looking for the limiting reactant. You know, the limiting reactant is the one that makes the reaction stop. It runs out first, can't get past that amount. It limits it. So let's do this one. Potassium superoxide is used in rebreathing mass to generate oxygen according to the following reaction. If the mass contains 0.15 moles of KO2 and 0.100 mole water, is a very popular reaction. How many moles of oxygen can be produced? So how many moles of oxygen can be produced? What is the limiting reagent? And we use the term reagent and reactant interchangeably. So what's the limiting reactant here? Let's do it. So to do a limiting reactant, when you see this for limiting reactants, you want to think as soon as you know you're looking for limiting reactant or you need limiting reactant, you want to think 2 conversions, 2-dimensional analysis, 2-unit analyses. Okay. Let's do 2 of these. Okay, so here we go, and we set up this to do both of them. So let's do it with what we have. Let's start with the KO2. So we do 0.150 moles as my given of KO2. And what I'm looking for to see which of the, to get to moles or grams. Now, typically people like to run these all the way to grams, but you can stop at moles. So when you see your answer, you can stop there. So we're just going to go to moles because we know compare mole to mole, right? So we take the moles of this and we're going to automatically say a mole here. I'm going to go mole here of KO2. Okay. And boy, I can go directly mole to mole of O2 gas. And so I'm going to use the amount of O2 gas as an indicator, right? So whichever gives me the least number of moles of O2 gas, that's the limiting reactant. So if I do this, I would then put in whatever I see in the balanced equation. In front of KO2, I see a 4. It's whatever you see, nothing more than that. In front of oxygen, I see a 3. You don't think of anything. You only write what you see in the balanced equation. No thought process really that deep at all. Just write what you see. So if you do this, you'll come out with 0.113 moles of O2. And so that's correct for right number sig figs. So let's do this with water. So this is 3 sig figs also. How do I know? I know how to count my sig figs. That's how I know. This is going to be water. So times, I'm going to put moles of water automatically on the bottom because I see it right here. Then I'm going to go moles of O2 equals. So I look at what's in front of oxygen. There's a 3 in front of oxygen. In front of water, this is H2O. In front of water, I see a 2. I simply write those values. I put this in my calculator and punch it through, and I get this number of moles of O2. Since this is the smallest amount produced, the limiting reactant, therefore, your limiting reactant, term reagent is used interchangeably, equals, what do we, K2, because it gave the least amount out. That's my limiting reactant. Okay. Let's do one more here. Let's take a look at this particular one here and see what we can do with it. So suppose 13.7 grams of C2H2 reacts with 18.5 grams of O2. According to the reaction below, what is the mass? So in this case, we want to know the mass of CO2 produced. All right. And so when we ask that, again, anytime they ask that and you have two reactants and you have quantities, mass for both, you have to do two analysis. Two. Okay. All right. And what's the limiting reactant? So let's just do this with both of these. Let's start and do this with 13.7 grams of C2H2. That's my given. Automatically, I put grams here. And automatically, I put moles here because that's the only way it can go. It can't go by any other route. Now I can start to think a little bit. I have moles of C2H2, which I can take directly to moles of, what am I looking for? CO2? CO2. All right, then I can take these moles because it asked me for grams. I should have written that out here so I can keep an eye on grams of CO2. Just want to make sure I don't lose track of that. So I automatically, I have moles here. I automatically put moles on the bottom. Moles of CO2. And then we can go to grams of CO2. And that looks like that should work out pretty good. If you notice, I don't really cross these things out. It gets a little too messy for me on my paper, but you can cross things out. And you can use these hash marks that some like to use that look like this. I'm not fond of them, but they work. Okay, so now we just come back here and we will put in the values where they make sense, right? Okay. All right. So let's see. Yep, there we have it. We have grams. We have to do the molar mass. This is molar mass. Molar mass. We get this from the periodic tables sum. And so if you add these values up for this, you get 26. Get about 26. We'll call it 0.00. A few decimals moved here or there. I mean, a few decimal points. The actual number should be about 26.04, something like that, we'll call it. Okay. And so mole to mole, where do we get this from? We read it from the balance equation. I see a 2 here. In front of CO2, I see a 4. I don't try to reduce them. I don't try to do anything. I simply read them and put them in there. And CO2 is, I think, 44.00, 44.1 gram per every 1 mole. If we punch these numbers through, we get about 46.3 grams of CO2 from C2H2. Okay. So let's see how much we get from the other reactant. We have what? Oxygen. Okay, so we have 18.5 gram of oxygen. We do a similar dimensional analysis. Gram automatically goes on the bottom. The moles of O2, and this is gram per every 1 mole. So this is 32 gram per mole, 16 plus 16 gram per mole. And then here we go, mole on the bottom, mole O2, and we're trying to go to mole CO2. And we simply read what's in front of them. In front of the CO2, I have a 4. In front of the O2, I have a 5. So this is going to be times the same molar mass, going to be mole automatically because I see it on the top. I write it on the bottom. Then it goes to gram CO2. And the molar mass of this, we already had it somewhere. Yep, 44.00 gram per every 1 mole. If we punch this number through, we get 20.4 CO2 from O2. Therefore, O2 is a limiting reactant. Okay. Okay. because we get the least number of grams from this. This should be grams right here, grams from that with the right number of significant figures. All right. So that's it. That's how we work problems involving these limiting reactants and these reaction calculations.